Hi, I'm Adam. Welcome back to Godot Game Lab. In this episode, we'll implement UnitNavigation. So if I start buying some units and put them inside the board, start a new battle, and if I press enter, you'll see that the UnitNavigation system is initialized and all of these tiles are marked as occupied ones, as obstacles basically. And I can press two buttons. Q will start moving one of the player units towards a random enemy unit. And indeed, if I press Q, Björn starts moving and you can see that the line is drawn between the target and Björn. If I press E, we'll do the same for an enemy unit. And these can be moved independently from each other, and you can see the navigation system updating in real time when the unit moves. If they reach their target, the paths disappear, indicating that they could start attacking each other. That's what we'll implement in this episode, but before we actually jump into the implementation part, this time I've included a pretty long discussion if you're interested in how I arrived at this solution and a bunch of other things. This is sort of a warning. If you're only interested in the implementation and the solution, feel free to fast forward to the architecture overview part. Even before we jump into the architecture overview part, I want to digress a bit and talk about pathfinding and the struggles I had with implementing the unit AI, just in general. The reason why I do this is I think it's interesting and also sort of just to give you a realistic view that even if someone is quite experienced like me, you can still struggle a lot with specific topics or features you want to implement for your game, and that's perfectly natural. So I don't just want to present a solution to you which may come off as like something I can do in a heartbeat, but that couldn't be further away from the truth actually. So the first kind of version I wanted to do uses an algorithm called context steering behavior, and this is an earlier build of the game which tried to make this solution work. So if I put in some units, go into a battle and start the pathfinding or the battle logic, you can see these raycasts, and the green arrow indicate that they can go towards a specific direction when they choose an enemy, and the red arrow indicates that this direction is blocked. And you can see that it kind of works, right? Why didn't I go with this solution? Well, because I had some weird edge cases which I couldn't really figure out really. In this case, we had no errors again, finding the enemies and the players, but sometimes if I keep swapping them around, some units would get stuck with all the possible directions blocked. Okay, so finally we hit one. So the unit is essentially stuck at this position, and that's not really what I want. And the naive solution would be to do raycasts in the other direction as well, so they can walk backwards. But the problem I run into with that version was that they would just start dancing back and forth, right? So they move to the left, and now the right raycast would be free. So they move back to the right. Okay, now the left raycast is free. It essentially yielded the same result because they would be still stuck, just dance back and forth between left and right movements. I felt like there must be a better solution than this. Context steering behavior is still a useful algorithm to have in your toolbox, but for this specific use case, it just didn't work. By the way, I use this awesome website from Kids Can Code called Godot Recipes, and that's where I had the idea coming from. So there's a really cool text-based tutorial with a video version as well, explaining how this context-based steering algorithm works. The example that's given here is used for a racing kind of game, but I was like, okay, this still can be applied to the game we want to make, right? Turns out it couldn't really, or maybe I just missed some crucial additional steps or something, but I couldn't really figure it out or make it working in a way that there weren't any edge cases. At this point I was pretty desperate, and I even contacted the developers of Tales and Tactics, which, if you don't know, is a single-player AutoBattler game, which is quite fun, honestly. I sank a good couple of hours into this game, and on the website of the developer, I saw that you can contact them and ask questions if you want to. So I started emailing with one of the devs of this game, and he was pretty helpful, actually, and really nice with the whole thing. So he gave me a vague or a general idea of how it's implemented in this game, but it's made in Unreal Engine, but it's a pretty different engine compared to Godot. So he just gave me like general pointers and ideas how to implement it. So what I ended up using is not exactly the way it works in Tales and Tactics, but I think the end result is pretty good. I ditched the context steering behavior and used an A-star algorithm. This is a built-in pathfinding algorithm that's readily available in Godot, so you don't really have to know the theory or how the algorithm works exactly. You can just kind of use it in Godot because it's part of the engine, so you can use it. I would still recommend reading this very good, very thorough article. It has a lot of visual examples, even interactive ones, and explains exactly how this A-star algorithm works. It's a pretty commonly used algorithm for Unit AI and pathfinding in general. Super cool with like animations that you can step one by one. You have pseudocode explaining how this works. So it's a super cool website. I definitely recommend checking out this article if you're interested in how the A-star algorithm works. But all you have to know really is that it's built into Godot. So what we will use in the example project is the A-star 2D and the A-star grid 2D classes. So we have two of them actually in Godot. The A-star 2D class is the more general one. And the description in the doc says it's an implementation of A-star for finding the shortest path between two vertices on a connected graph in 2D space. So yeah, you have a bunch of methods exposed, adding the points and connecting them, clearing the whole graph and things like that. But in our case, it's even easier or more specific than using this because we have a 2D grid, a rectangular grid. So we have a more specific class called A-star grid 2D, which handles connecting the points by itself on a rectangular 2D grid. So we don't have to manually connect the nodes of the graph like in this image. So for the A-star 2D class, you will have to add these points manually and establish the connections between them. So let's say this is point 3 and this is point 4. You have to add both of those with the add point method, and then you have to add the edge between them, which is the connection. And you have to do this for all the points. The upside of this is that it works for any kind of graph, like this one, which is not really regular per se. But the A-star grid 2D, it's a rectangular grid where all points have 4 neighboring points, right? So it's super useful for a rectangular grid because you don't have to do anything. You just have to provide the region, which is the size of the whole rectangle. And then you have to provide the cell size, which is the size of one point inside that grid. And then the rest of it will be handled by the engine. So this is what we use for this project, right? Because it's perfect for our use case. One other thing you might be interested in, and I often get comments about this, is what about hexagonal grids, right? Because Tales and Tactics uses hexagrids and a bunch of other AutoBattler games. Well, you can use hexagonal tiles with the tile map layer node in Godot, and you could use the A-star 2D class to manually set the neighbors, because for hexagrids it's different, right? Because each tile has 6 neighbors. And you could use the A-star 2D class to manually add all the points and the connections, which is perfectly fine and a good learning experience, but there is a plugin, or I believe there are multiple plugins, but this is just an example one, which creates this A-star hex grid 2D class, which you can use readily made. It's just one GD script really, because all you have to do is to set up the hex grid, and what's abstracted out or turned into a plugin is actually setting up those connections I was just talking about. So if we take a peek at this code, you'll see that setup hex grid will connect the hex point. So this is the main method that you have to implement either by yourself, or you can use a plugin for that if you want to do hexatiles, right? It still uses the tile map or the tile map layer node under the hood because, as I said, Godot can handle hexagrids. It's just a matter of connecting them with a new A-star 2D instance. So that's about it for the theoretical background for this whole navigation. I'll leave the links for all these articles and documentation pages that I've shown you here in the description. So how do we implement the unit navigation system? First of all, we'll have a custom node, a new one called UnitNavigation. And you can see in the parentheses that this will be an auto-loaded class, which is pretty uncommon in my tutorials. But we'll get back to that in a second. So the UnitNavigation node will will be used by the battle handler, and later on, when we implement the unit AI, it will be used by the AI to calculate the path to its current target, and namely we will have different states, and in the chase state we'll use this unit navigation system. What about the other way around? So which systems or nodes or parts of our project does the unit navigation need in order to work properly? It needs the game area, which, if you remember, is a play area, which is a custom implementation of a tile map, providing a bunch of conversion methods between tile coordinates and global positions. And it also needs the battle unit grid, which we just created for the battling units. Also, if you remember, the battle grid contains both the player units and the enemy units. And of course, this is important to have access to the current state of the board, because we need to mark the occupied tiles as obstacles for the navigation. In itself, that's not a really complicated diagram by any means, but probably the most interesting part is why I ended up going for an AutoLoaded class for the unit navigation system. So let's take a look at the reference project I have open here. So we'll have the unit navigation node somewhere in the project. I ended up using an AutoLoad, so it's not visible here. Remember the diagram. So we have the battle handler, which will use that functionality, and we'll also have the unit AI, which will need to have access to the unit navigation. So where will the unit AI be? We have the battle unit grid, which will instantiate battle units, and if, just to show you, we instantiate one, tick editable children, so we would have multiple battle units, right, under the battle unit grid. So there would be a component attached to the battle unit called unit AI, which we don't have yet. Let's just imagine that this is this one. Or you know what, we can add the node to it. It's not a big deal. Click on the plus sign, add a node, and let's call this unit AI, right? So we would have multiple battle units with the unit AI attached to them. So this node needs to have access to the unit navigation system for the chase state, but also the battle handler. And see, the problem or the dilemma I had is that these are really, really far away from each other in the scene tree, right? If we collapse the game area, the battle handler is directly under the arena, the root node. And for the units AI, we have to go pretty deep inside the game area. We have the battle unit grid, we have the battle unit, and then we have the unit AI. And probably even more nodes if we want to have a node-based state machine. And we could do dependency injection, say that, okay, the unit navigation system will be next to the battle handler. And for the battle handler, it's not a big deal to have access to an adjacent node. We do this all the time with the other ones. We can just use export variables like here, but for the units themselves, it's pretty far away. One thing we can do is that we know that the battle units will be instantiated dynamically exactly by the battle handler. So if we provide that access to the battle handler, it could inject the dependencies for all the units, right? And yes, that's a working solution, but we also need to think about providing the dependencies for the unit navigation. So if you remember the diagram, we need to have access to the game area, which again wouldn't be a problem really because this would be adjacent. So we could use an export variable, and really the same is true for the battle unit grid. I'm not using an AutoLoad because it's a must for this solution to work. I just want to show you as many techniques and alternatives as I can. While export variables work perfectly fine, let's talk about the other side of the coin, the AutoLoads. So what's the main downside of using an AutoLoad for things like this? Well, it's that when we have any systems that rely on having the unit navigation or access to the unit navigation, we couldn't test them in isolation without having access to the unit navigation. So we create this tight coupling between the unit AI, the battle handler, and the unit navigation, right? Because we can't test the battle handler without having access to the unit navigation system. Now, the question I would ask in this case is that really such a big issue here? When would I want to test the unit AI without having access to a unit navigation? It doesn't really make sense because it does need that context in order to be testable, right? Like, how else would I test the unit navigation system? So I'd argue that in this case, it doesn't really matter which solution you choose. Both of them are equally fine. And I noticed this trend of demonizing singleton classes or autoloads a bit, mostly because when beginner devs discover this technique or this pattern, they tend to overdo it. So there are cases when it's actually bad to create this tight coupling. I just don't think that this is such a case here. So my main argument is not that it's the best solution, it's just that I want to show you different ways to do the same things throughout the two courses, the Slate Aspire course and this one. And while dependency injection is fine, I think autoloads are also fine in this case. So that's my argument for the solution that we will implement in this episode. Now we discussed this whole navigation thing inside and out. Let's see how we can actually implement it. Okay, I have the project open here, and the first thing I want to do is to go to the file system doc and create a new custom node. So let's right click on this folder, create a new script, and we'll call it unit_navigation.gd. Click on create and double click to open it up in the script editor. So remember, for auto-loaded classes, we don't have to use a custom class name because this will be handled by the engine. So the first thing we do instead is we provide a custom signal called pathCalculated, which will emit when one of the units will have a path calculated towards its target. And we'll have two parameters passed to this signal. One will be an array of points for the path itself, and one will be the moving unit. In this episode, we'll only connect to this signal for debugging purposes so we can draw the actual paths to the screen. Then we'll have a bunch of variables. Two of those are the external dependencies we were talking about during the architecture overview. Then we'll have a variable for the A*Grid2D instance we'll create, and one rect2i, which will be the size of the game area, so it covers the whole part of the arena where the units can move. Then we'll have a custom function called initialize for setting up the unit navigation. We will handle this inside the arena node, the root node, so when everything is ready in the scene tree, we can initialize the navigation system. And to do this initialization, we need to inject the external dependencies, the battle grid and the game area, right? Because those are the two things we need from the outside in order for this navigation system to work, which will be stored in these two variables. And we do exactly that. We inject those dependencies and store them in the variables. And then we can create the A*Grid2D itself and initialize it. So we can set the full grid region variable when we have access to the battle grid, because we know the size of the battle grid, right? It's an export property. So we just create a rectangle from 0, 0 with the size of the battle grid. Then we create a new A*Grid2D instance and set a bunch of properties we need for it to work. One of those will be the region where we implement the pathfinding. Then we have the cell size, which we'll use the arena cell size constant for. And we can set this diagonal mode property. And for this game, I opted for a version where units cannot move diagonally ever. So if we press and hold Control and click on diagonal mode, it will open up the documentation page, and we can see that a specific diagonal mode which will force the path to avoid or accept the specified diagonals. And if we click on this enum, you'll see that we have a bunch of different properties we can choose. All of them are pretty well documented. We just chose this version of ignore all diagonals. Then we call the update method, which will update the internal state of the grid, which will make it ready for pathfinding, right? Because we have all the properties set up. And it even says that when the cell size, the offset, or the region changes, you have to call this. Well, we changed the region and the cell size, so we better call it, right? And we also connect to the battle grid's unit grid changed signal, because in this case, we have two kind of cells in the game area. We have free cells where the units can move to, and we have obstacles which the unit needs to avoid. And what we consider obstacles in this pathfinding is actually units occupying tiles, right? So when the unit grid changes for whatever reason, for example, when a unit dies, then one tile will be freed, right? It will be free to move to. So that's why we need to connect to this signal. So what do we do inside this method called update occupied tiles? It will be pretty straightforward. We call the A*Grid's fill solid region method, and what this does is it fills the whole grid with a specified value for the solid flag. So solid means obstacle, right? And not solid means free to move to. So what we do is when we update the occupied tiles, we set the whole region to false, meaning that all the tiles are free to move to. And then we iterate through all the occupied tiles that we have stored in the battle grid and set those to solid. So this is only temporary. So we clear the whole thing basically and say that, okay, all the tiles are free to move to. And then we take all the actually occupied tiles that we store in the battle grid and we set those to solid to say that, okay, these really are obstacles because units are standing on that tile. And then we have the most important method called getNextPosition. And we need to have a moving unit which wants to do the moving or the navigation. And we need to have a target unit which the moving unit wants to move towards, right? And we return a vector 2 for the new tile coordinate where the unit can move to. This is the bread and butter of the whole thing. This will be used by the chasing AI later on. So the first thing we do is we want to grab the tiles that the units are standing on. And this is why we need to have access to the game area as a dependency, right? Because it's a play area, and if we press and hold Control, we have this method where we can grab the tile coordinates from a global position. And this is exactly what we want to do here. We take the global position of both the moving and the target units and just convert it into this game area tile coordinates, which are the same that we have in the A star region because they have the same size. So we have both the unit tile and the target tile available. And I even included comments just to break the logic down further. The first thing we want to do is that if the unit finds a proper position that they can move to, the moving unit, then we need to remove that as a solid, right? We need to remove it from the battle grid as an occupied tile. So what we do is we say that, okay, if the unit can start moving, this won't be an occupied tile anymore, won't be a solid. And then we can rely on the A star grid to find the path between the unit tile and the target tile. And the reason why we have this true parameter here is a bit of a tricky one. So if we press and hold Control on the get ID path, we can take a look at the documentation. So it says that this returns an array with the IDs of the points. ID just means coordinate in this case, a tile position. So the IDs of the points that form the path found by the A star 2D between the two given points. The array is ordered from the starting point to the ending point of the path. If there is no valid path to the target and allow partial path is true, returns a path to the point closest to the target that can be reached. Now think about this for a sec. If we go back to 2D view and run the game, if I want to calculate the path between these two units, right, then this will be the starting point and this will be the end point. But the problem is that according to the system, this point, the end point, is occupied, right? It's an obstacle because a unit is standing on it. If we do this by the strict definition, then we can say that there's no valid path between the two units because I cannot reach this tile ever because it's an obstacle. So I cannot move on it. Hopefully that makes sense. And what this allow partial path does, it does the heavy lifting for us. It says that if it's true, it returns a path to the closest to the target that can be reached. So in this case, this unit could go in this path, but this is blocked, right? But this, however, this point right here above the unit is not blocked by anything and it's the closest that they can go to. So with this allow partial path property, the path will be calculated from here to here, right? Like this L shape. And this is absolutely what we want. And it does a bit of a heavy lifting for us because otherwise we would need to do this by hand, which is not the end of the world, but it's a bit tricky because how do you pick the closest available point? You have to take a look at all the four neighbors, right? Need to see which is the closest one that's not occupied. So this would be a bit of a pain or harder to implement on our own, but luckily for us, we have this built in. So by default, it's set to false because most of the time you call this method by picking an endpoint which is not occupied. But in our case, since units do take up space, it makes sense to set this to true. And it says that when allow partial path is true and 2ID is solid, which is true in our case, the search may take take an unusually long time to finish, but I haven't really experienced this at all in my playtests. So this is why we need this true here. Hopefully that makes sense. And when we do have a path, we can emit the signal that the path was calculated for the moving unit, because this returns an array of vector 2i's. And that's fine, but it can happen that actually we cannot move anywhere. When does this happen? Think about a scenario like this. If for whatever reason Björn is the one who will calculate the navigation first, then he cannot really move, because even though this tile is empty, remember we cannot really move diagonally. This is an obstacle, this is an obstacle, and if we want to move to this tile, then we don't really have a valid path, right? Because we cannot move to the right and we cannot move upwards either. And we have to handle this because, yes, we call the method, but it will return a pretty empty path with just one point, the starting point, added to it. So it can happen actually that a unit is stuck when we want to calculate the position. So this is what we handle in step 2. See, when there's no adjacent tile next to the moving unit, we stay there and add it back as a solid. Because remember, we just said in the previous step that, okay, if we do have a path and we will move the unit, then we can say that the tile we are standing on is no longer an obstacle. Well, if we cannot really move anywhere, then it is still an obstacle. So we need to set it back. So what we do is we check if the array that provides all the points from A to B, from the moving unit to the target, only has one point, and that one point is equal to the tile we are starting the movement from, then we can confidently say that this path is actually empty. So what we do is we set it back to an obstacle in the A star grid and return from this method immediately, because we want to provide a valid tile position where we can move the unit to, but we don't have one. I decided to signal this by convention to -1, which means that when we handle the unit AI, we can check for this -1, and this will mean that the unit doesn't have a valid position to move during this AI tick. When we arrive to this final step, it means that there is a valid path, and we want to update the grid and set the next position to solid and return the coordinates. Since this get ID path returns all the points, all the graph nodes in the path from A to B, we only need to grab the second one actually, which will have the index of 1. And what we do is we manipulate the battle grid. So we remove the unit from the original tile, we add it back to the battle grid, the same unit, but to the next tile we want to move to. And we also set the point to solid in the A star grid, signaling that the unit already occupies that next space. And remember, this will trigger recalculating the whole thing. So this might be a bit superfluous, because when the battle grid changes, it will emit the unit grid changed signal and we redraw the whole thing. But just to make sure we can do the same thing here, make sure that it happens immediately after we add the unit to the battle grid. And the very final line of code we need here is returning the position where the unit wants to move to. We could either return the tile coordinate or the global coordinate. I decided to return the global coordinate just to make it easier for the AI implementation, right? Because when we actually want to move the unit, we don't really care about which tile coordinate the new position has, because we already handled this here, adding it to the battle grid. So when we just want to do the tweening or moving the unit, it's easier to work with the global coordinate. So we use the game areas get global from tile, we pick the next tile, we have from the pathfinding, convert it to a global coordinate and return it from the method. And that's really it. That's the whole point of the video, 50 lines of code. Hopefully it makes sense. It's not too complicated. A-star grid 2D and the A-star 2D classes are really convenient and really make it easy to implement this kind of pathfinding in your game. We just need to save this and provide a way to hook it up and actually test it inside the game. So that's what we'll do next. If you like my content, please consider checking out my Ko-fi page, where you can donate one time or become a member and get early access to all my content and videos. Okay, so how do we test this? The first thing we want to do is to actually add it as an auto-loaded singleton, because we haven't done it yet. So let's go to project settings, go to globals, and click on this folder icon to browse for the node we just created, go to custom nodes, and we want to do UnitNavigation.gd. UnitNavigation is perfectly fine as a node name, click on add, and now we have added as an auto-loaded or global singleton. we can close the project settings and actually hook this up, because remember we have this initialize method where we need to inject the dependencies. And if you remember, I said that we'll do this inside the arena. So let's press Ctrl-Alt-O and search for arena.gd. And inside the ready, we have the music player.play. And what we can also do is UnitNavigation.initialize. And we need to have access to the battle grid and the game area. And we have this error message because neither of those are referenced. Let's just drag and drop those in as already variable references. For the game area, I just drag and drop it, press and hold Control, maybe rearrange it a bit. And we do the same for the battle unit grid, press and hold Control, drag it over. We could do export variables as well, it doesn't really matter. I don't think that the hierarchy will change that much for this arena. And I think the names don't really match because I just use battle grid as a variable name here. So we can just make sure that those two are matching, right? And we have the error message disappear. Okay. So now we initialized it. So when we save this with Ctrl S and run the game, we can still drag units around by XP, start a battle, but nothing really happens because we haven't tested this navigation system yet. So the next step would be to provide a debugger for the unit navigation system, just so we can see how the whole thing looks a bit better. So let's go back to the view. In the file system doc, we can create another custom node, create a new script, and we'll call this unit navigation debug. And let's make sure that it inherits from node 2D because we want to draw stuff on the screen. This time, click on create, double click and open it up in the script editor. Okay, so we'll do a bunch of cool stuff with this debugging class. The first thing we want to do is provide a custom class name, and I just called it unit navigation debug. And we'll have 3 export variables, one for the play area, again for this global to local coordinate conversion, and we'll have a color for the obstacles, which we can set, and we'll also have an array of colors for the paths. So we can have multiple colors, which we can cycle through to make sure that the crossing paths are easier to distinguish between. Then we'll have a dictionary called paths, which will be empty by default, and inside the ready callback, we will connect to the unit navigation's path calculated signal. And if you remember, what we do here is we emit this signal when we calculated the next path for a moving unit, pass the battle unit as a parameter and the array of points for the path. Then, which is pretty cool, and I think we haven't mentioned it in any of my tutorials, we'll override the draw virtual method. And what this does is it allows us to call methods that draw different shapes and lines on the screen, right? So you can do this to draw any custom debugging tool, really, or even draw things for your game. And what we do first is we cycle through all the coordinates that are available inside the unit navigation's A-star grid. We'll query all the coordinates, and if they are solid, we want to draw a rectangle, which will be the size of the arena cell size, and will be at the position of that ij multiplied by the cell size. So this will draw a rectangle that covers that tile where a unit is standing, and we'll use the color export variable for the color of this rectangle. So this drawRect method is one which we can use in the draw virtual method to, you guessed it, to draw a rectangle. Of course, it will be useful to use a semi-transparent color for this so it doesn't cover the whole unit standing on that tile. And that's one part of the problem, but we also want to draw the paths for the units where the pathfinding is activated, right? So we'll iterate through all the current paths we have inside the dictionary. So this is a dictionary that we will update when this signal is emitted, but we don't have that method yet, right? So we'll have arrays of points connecting one unit to its target, and we'll iterate through each of those paths, and we'll call this drawPath method, which we are yet to implement, and we'll pass in the path, and what we do is we use the path colors and we'll pick the current one. So we have an I integer which starts from 0 and it's added to 1 after each of the paths drawn, and we wrap it between 0 and the size of the array minus 1. So if we have 4 colors, then the indices will be 0, 1, 2, and 3, and what we do is for each path we'll cycle through the colors. So the first path will be color 0, the second will be color 1, and so on. And when we reach the end of the array, we'll start again from 0. Then one. So this is how this rep_i function works. So this draw path method will need two parameters, the path to draw and the color to use. So we have two methods that we are yet to implement, and we'll also override the input callback because the draw method won't be done in every frame by default. So you can control how often you want to redraw these rectangles or these paths we have inside the draw method. And to make sure that we can see what it looks like from the beginning, when we press UI accept, which is the enter key by default, we'll queue redraw. So this will trigger redrawing or calling this method again. The draw path method is pretty simple. We have the points we want to draw and we have the color we picked here. And then we iterate through all the points, and notice that we start from the second one, right? Because we reference the previous one with i-1. And what we do is the from position will be the global position of the previous tile, and the to position will be the global position of the current tile. And then we just call the draw line method, which is similar to the draw rect. It takes two coordinates we want to connect with the line and the path color. We could also change the width and a bunch of other things. So if you press and hold Control and click on the draw line method, you'll see we have the width and we have a property for it to be anti-aliased. You can play with these parameters if you want to. The default one will be pretty visible. And finally, we have this callback method when the UnitNavigation AutoLoad class emits the signal of having a path calculated. And what we want to do when a path is calculated is set it inside the dictionary for that specific unit, which means that it will be updated if we have a newer path compared to a previous one. So if the unit moved one tile, then because we have the unit as a key in the dictionary, it will be replaced with the new path. And then we call the queue redraw. So every time a new path is calculated, it will redraw on its own. Pretty cool, right? That's all we really need for the debugging system to work. Let's save this with Control S and let's see how it looks like in practice. And if we go back to 2D view and collapse the scene tree a bit so we can see the whole thing, select the arena, click on the plus sign and search for UnitNavigation debug. Let's drag this up to keep things organized, and we need to set the export variables. So for the occupied color, I just use maybe some red and make it semi-transparent so we can still see the units. For the path colors, I will cycle through, 5 maybe, and just pick very different colors from each other so we can see. I use very vibrant and different colors so we can see the paths for the units. Let's use a bright red as well, or orange. Let's use a green one. Let's do maybe a yellow one as well. And for the last one, let's do pink. Okay, so we have 5 different colors and we will cycle through those. And for the game area, we can just assign it from the inspector. Awesome. Now let's save this with Control S. And if we play the game, drag a couple units in. And you see that when we start a battle and I press enter, something happens. We'll see the occupied tiles, and it's kind of right because you see that there's 2 units here, 1 here, and we have this pattern, but the whole thing is out of place a bit, right? And the reason why is because this is a node 2D, and you see the position is at the top left corner of the screen. So if you go to move mode by pressing W, turn on grid snapping and configure the grid because this doesn't seem right. The grid step should be 32 by 32. Yeah, so now if we move it to the same place where we have the game area, you see the same position is applied. We can even lock it so it cannot be moved. And if we save now and replay the game again, start a battle, press enter, and you can see that the initialization of the UnitNavigation system works perfectly fine because we only draw these rectangles when we have obstacles registered inside the A-star grid 2D or solids. These are considered solid and they need to be avoided when calculating paths. Awesome. So now we just need to somehow start instructing the units to move and do all kinds of stuff, which will be done in a future episode. So we don't start building the AI yet, but we can still get around to testing how the path calculation works. So the last thing we want to do is to actually do these tests. So how can we approach this? First of all, let's go back to selection mode by pressing Q. And what we want to do is we want to use the battle handler node for this, because that's where we have access to all the units and spawning them and such. So let's click on the script icon next to the battle handler, and we'll introduce a bunch of testing code. First of all, we'll add 4 new variables called player test, enemy target, and player target. We'll use these to cherry pick units and test their navigation inside the game. Then we'll replace this input test code we have. So instead of queuing free all the units, we'll do the navigation stuff. So how does it work? If we press the test 1 action, we'll grab the next position from the UnitNavigation singleton using the player test and the player target variables. We'll check if it's -1, because remember, this means that this unit cannot move anywhere because all of the available adjacent tiles are blocked. If that's the case, we can return from this method immediately. But if it's not -1, we can tween the global position to this new position for 0.5 seconds. And we'll do pretty much the same for the test 2 action, but for the enemy unit, right? So we can test it. And the final thing we need to do is to actually set these variables, right? Because these are null. So inside our prepare fight method, when we set up everything, we can just add 4 lines of code and see we'll grab the second one from the player and the enemy units. And for the target, we just take a random unit from the opposing group. So the player target will be picked from the enemy units and we pick a random one. The enemy target will be picked from the player units and again, we'll pick a random one. And that should be enough to test our navigation system. Let's save this with Ctrl S and play the game again. So if we put a couple of units in, maybe like so, we press enter, you can see that the solids are set. And if I press Q, I believe that will move the player unit. Yeah, so Robin started moving and you'll see the path drawn. And the target is probably this unit, right? So if I keep pressing Q, you'll see the path recalculated every time. And you can see that the obstacle avoidance works, right? And setting the new solid also works. As soon as Robin starts moving, you'll see that the target tile will be occupied. If I start pressing E, nothing happens because they probably had the same target. Let's play the game again. See if it works for enemies. I'll start pressing E this time. Yes. And you can see if I press Q, we'll cycle through the different colors so they won't be blocking each other. And I can keep cycling forward with the UnitNavigation system. And the lines essentially disappear, but that's not a problem because this distance, even for melee units, would mean that they would start attacking each other, right? One interesting test case is what happens when we block the unit. So we saw that this is the unit I start moving when I press Q. And if I press Q, I keep pressing Q, but you see that there's no real path drawn because both of the available positions are blocked. So if I keep pressing Q, nothing happens because we get that -1 coordinate. But if I press E, you'll see that the other unit starts moving around and it can still move independently from the other one. Awesome. And when we are 100% sure that this works, we can get rid of all the testing code, or you can leave it in as you like. You just need to delete these 4 lines, scroll up, you can delete the input event callback, and also these 4 introduced variables. Save it with Ctrl S and we should be good to go. The UnitNavigation system is up and running and we can use it to actually start implementing the AI for the units in the next episode. That's it for this one and I'll see you in the next one. Bye bye.